So today we're going to be looking at how we can use a schematic pressure volume diagram with isotherms to determine the A and B parameters of the van der Waals equation. So the first thing to note here is that as opposed to our typical phase diagram with temperature along the x-axis and pressure along the y-axis, we actually have volume along the x-axis. And this isn't your typical volume. This is actually the specific volume of the substance. Another way to put this would be it's the inverse of the density. And all this is the volume per mole of the substance that we're looking at. Another thing to note on here is that, as you can see, there's several different curves, and each of these curves corresponds to a specific pressure. So since we're not looking at temperature anymore, each curve represents the pressure and the specific volume at a given temperature. So for example, this curve right here is when the temperature is at the critical point, which the critical point is marked by the C right there. These two curves are when the temperature is below the critical point. And then this top curve is when the pressure is the temperature is above the critical point. So if we want to see how this looks in 3 dimensions real quick, just so we can get a better understanding of it, we have temperature along this axis, volume along this axis, pressure along this axis. And as you can see here, when you take the temperature and pressure axes, you get a typical phase diagram. And then when you have the pressure and volume axes, you get our pressure volume schematic. But the important thing to note is that as you go through these temperatures, the curve looks different. For example, right here, this is when the temperature is at the critical point, which is shown here. But if you were to take a curve further down, say this temperature right here, it's going to be a different diagram. That's why on our schematic up here, we have a bunch of different curves. These are called isotherms. So let's look at a few more things before we get started finding the parameters A and B, just so we can get a better idea of what we're shooting for. So the first thing to notice is that if we were to extend one of these isotherms out really far down along the volume axis and really far down the pressure axis, we would notice that the substance starts behaving more and more like an ideal gas. The reason for this is that an ideal gas pretends, or an ideal gas law pretends, that the molecules of gas don't take up volume and they don't interact with each other. So if we were to look at the equation PV equals RT, or the ideal gas law, for 1 mole of substance, when there's no N, that obviously means N equals 1. We will notice that the equation doesn't account for the volume that these molecules of gas take up. What the van der Waals equation does is it accounts for this volume, and it also accounts for the attraction that the molecules of gas feel for each other. So the last thing I'd like to look at before we get started with the van der Waals equation is this little region right here. And this region is empty. All it's saying is that, well, at a specific temperature and pressure, we have the specific volume of vapor, and at a given pressure and temperature, we have a specific volume of liquid. There's not a phase between liquid and vapor, and this is when the liquid and the vapor are in equilibrium. So the space in between is empty, and we just have the specific volume of the liquid phase and the specific volume of the vapor phase. So now that we've looked at our schematic pressure volume diagram, we can actually take a look at our van der Waals equation. So the van der Waals equation, and I'm just going to call it VdW just for simplicity's sake, takes the form of pressure equals R times temperature over our volume minus B, and B is the excluded volume, meaning that it is the volume that the molecules of gas take up themselves, minus A over V squared, and A is an attractive force. So when these molecules of gas interact with each other, there's an attractive force between them because of dipole-dipole interactions. It's also important to note that these V's are, again, specific volume. I believe the actual notation of the van der Waals equation has a small m there, just to indicate that it's for 1 mole of gas, but we're not going to write that down for now. So since we know that A is an attractive force, that's why this term right here is negative, because it's decreasing the pressure because if molecules are interacting with each other, they're not repelling each other, they're attracting each other, it's going to reduce the overall speed of those particles within the system and decrease the pressure. So another interesting thing is that we can actually solve for A and B using analytical methods instead of experimental methods. So if we look at our diagram here, we'll notice that at point C, and this is for the isotherm of the critical temperature, we notice that the slope is 0 because it's the maximum of this curve here. And it's also an inflection point because here we notice that the isotherm is concave up and here it's concave down. So the way that we can write this is that the derivative of pressure with respect to the specific volume at the critical temperature and at the critical volume equals 0. And since we know that it's an inflection point, that means the second derivative is also 0. So the second derivative of pressure with respect to volume at the same conditions, so temperature equals critical temperature and volume equals critical volume, is also equal to 0. From here, we can see that all we have to do is take the derivative and solve for A and B and set it equal to 0. And now we can just take the first derivative of pressure with respect to volume. And again, this is when the volume is at a critical volume, so we're going to have to specify that in our derivation here. So we can see that looking at our equation, once I can get it to scroll, there we go, we're going to have V minus B squared, and then we're dealing with a negative exponent, so this will become negative. We'll have negative RT over V minus B squared, and then we're dealing with another negative exponent, so this negative here will become a positive, and then we'll have V cubed in the denominator and 2A. So that is our first derivative. And then our second derivative of pressure with respect to volume sorry, I wrote that weird, is going to be, we're just going to go through the same thing. This negative, these two negatives are going to cancel out. I'll just go ahead and write it out so we can see it. And then V minus B cubed, and then this will become a minus again. And we'll have 6A over V to the fourth. And again, since we're dealing with volume at a specific volume, the critical volume, we just wanted to note that this is at the critical volume and also at the critical temperature. Oh, forgot. From here, since we know that both of these are going to be equal to 0, we can go ahead and make a system of equations. So over with the first derivative, we're going to have R times the critical temperature over the critical volume minus B squared. It's going to be equal to 2A over VC cubed, and then we can do the same thing over here. These two are going to cancel out, and we can see that R times the critical temperature, and actually there should be a 2 up here, I did forget that. So 2 times R times T, or the temperature at the critical point, is going to be, or over, sorry, I'm just stuttering over everything. The critical volume minus B cubed is going to be equal to 6A over the critical volume to the fourth. So here we can see that we're trying to solve for A and we're trying to solve for B. And since we have 2 equations and 2 unknowns, it's a pretty simple method to solve for each of them. We'll solve for one and then plug that into the other and solve for the other variable. So from here, it's some pretty simple algebra to solve for A and B. So first off, we'll solve for B. So what we're going to do here is we're going to multiply the left side, our first derivative, by the right side, our second derivative. And we're going to multiply it by the inverse, actually, I should say. So we're going to multiply that numerator by the denominator of our second derivative and vice versa. And so I'll just write it out this first time, but after the first time, I'm just going to simplify a bit. We'll end up with VC minus B cubed. So you can see how that gets there. Times R times our critical temperature. And then that'll be the same on the bottom. We're going to have our critical volume minus B squared times 2 times our critical temperature times R. And then you can see some of the terms cancel. These will cancel out, and then this will cancel out, and we'll be left with an exponent of 1. So I'll go ahead and simplify that. We'll end up with our critical volume minus B over 2 is going to be equal to, and then you can just trust me on this, or you can do it yourself, but we'll end up with the critical volume divided by 3. And from here, it's some pretty simple algebra. We just multiply both sides by 2/3. So we're going to end up with 3 times our critical volume minus 3 times B is going to be equal to 2 times our critical volume. And then if we subtract this to the other side, oh, that was a terrible arrow, we'll end up with negative 3B equals negative critical volume. And then we just divide by negative 3, and we end up with B equals our critical volume divided by 3. So there's B, and then from here, all we have to do is plug B back into our other equation and solve for A. From here, it's just some more algebra, so we're going to plug in our answer for B back into one of our equations. We'll use the R times the critical temperature. Actually, let me put my glasses on here. There we go. R times the critical temperature over V minus B squared, and sorry, that should be critical volume, is going to be equal to 2A over critical volume cubed. And then we just have to plug in B and solve for A. So we're going to get R times our critical temperature over 2/3 of our critical volume squared is going to be equal to 2A divided by our critical volume cubed. And then we just use the exponent. We end up with R times our critical temperature over 9/4 V cubed. And actually, let me rewrite this. We'll rewrite this as 9 over, or how about this? We'll rewrite it as 9/4 times R times our critical temperature all over our VC squared equals 2A over VC cubed. And then again, multiply through. We're going to multiply each side by this volume, or critical volume cubed. We'll end up with 9R critical temperature over, times our critical volume cubed over our critical volume squared. And then you can see that these exponents will cancel out, so we're going to end up with an exponent of 1. And that'll be equal to 2A. And then, I forgot a 4 over here, sorry about that. So we'll end up with 4 times 1 in the denominator. And then from there, again, pretty simple, divide both sides by 2. And we end up with 9/8 times our R times our critical temperature times our critical volume is going to be equal to A. So there are our equations for our two parameters in terms of critical properties. We have B is going to be equal to our critical volume divided by 3, and A is going to be equal to, and I can't remember it, so we're going to go back. We have 9 times R times our critical temperature times our critical volume over 8. From here, to get the compressibility factor, we know that our compressibility factor Z, let me write that a bit smaller. Z, that's like almost the same size, but that's all right. Z is going to be PV over RT. And then we know that our pressure is going to be equal to RT over V minus B, and then minus A over V. Let me double check that just to make sure I don't mess anything up. Of course I did. So A over V squared. And then if we're taking this at our critical temp or our critical point, we'll have our critical pressure, our critical temperature, our critical volume, and our critical volume again. And we can just plug in A and B. So we'll have our critical pressure is going to be equal to R times our critical temperature over 2/3 critical volume minus 9 over 8, and then this will be a bit long, R times our critical temperature times our critical volume over our critical volume squared. And then we can see a lot of things are going to cancel here. So we'll actually clean this up. We'll see that this will cancel, and then this will be an exponent of 1. Oh, didn't mean to erase that. And then we'll just have our critical volume, and there we go. I actually made 2 errors here. First off, this is not squared. No idea where that came from. And then we'll actually have 3 halves because normally this would be 2/3, and then since it's in the denominator, it'll be the reciprocal, so we'll have 3 halves. And then we can see here that both of these terms have this common term, R times our critical temperature over our critical volume. Let me get rid of those circles. So we can see that our critical temperature, or our critical pressure, sorry, is going to be equal to R times our critical volume over our, or R times our critical temperature over our critical volume times some constant, and then all we have to do is multiply by our common denominator. We'll have 12, and then minus 9, all that over 8, and then that's obviously going to be 3/8. So we're going to end up with our critical pressure is going to be equal to our critical temperature times R over 8 of 8 times our critical volume. And then from here, all we have to do is plug this back into our our compressibility factor equation and cancel out. So now something really interesting happens. Let me give me a bit more space. Actually, hold on, let me try something I've never done before. I am going to actually copy and paste something. There we go. Semi-surprised that worked. Again, so if we're going to do this at our critical point, we're going to be finding our critical compressibility at our critical volume, our critical pressure, and our critical temperature. And we have this equation for our critical pressure, so we're going to have our critical compressibility factor is going to be equal to 3/8 times our times R times our critical temperature over our critical volume. And then we're going to have our critical volume, and then the denominator will be R times our critical temperature. So from here, we have these two critical volumes will cancel out. So we're going to end up with, I'll give myself more space. We'll end up with our critical compressibility is going to be equal to 3/8 times R critical temperature over R times our critical temperature, and then these two will cancel out, and then we'll know that our critical compressibility factor is going to be 3/8. So the interesting thing about this is that you'll notice that there's no variables in it. What this is saying is that regardless of the substance, we know the critical compressibility factor is going to be 3/8. For example, if we were to have 3 times our critical temperature over 8, something random like that, this would be substance dependent. It would depend on the critical temperature of that substance. But since we don't have any variables in our final derivation of the critical compressibility factor, what we're saying is that the critical compressibility factor is the same for all constants. Or sorry, for all substances.